To predict complex, real-world sequential data, like financial markets or climate patterns, we need a rigorous mathematical framework. We have to find reliable structure inside sheer, unstructured noise. For the general linear processes we are defining, the core assumption is that the observed data sequence is driven by an underlying unobserved white noise series. We mathematically define this relationship using the general linear process, or GLP. This equation shows xt, our observed data series, assembled as a linear combination of wt minus j, those unobserved white noise innovations stretching into the past. The weights, represented by the psi parameters, determine how much influence past shocks have on the present. They govern the specific shape and memory of the resulting model. By truncating or manipulating this sequence of weights, we can derive two distinct classes of models, moving average and autoregressive models. Each carries a unique, identifiable statistical signature. Establishing this generalized linear foundation is algebraically necessary. It provides the mathematical constraints required to model historical data without breaking the underlying probability rules that make forecasting possible. The moving average, or MAQ, process is a strict truncation of that infinite general linear process. Instead of looking at the entire past, the current value relies only on the present innovation and a fixed number, Q, of past innovations. It has a finite memory. This is the specific MA1 model. Here, the current state relies on exactly one previous shock, scaled by a specific coefficient, theta1. We can extract the core properties of this model algebraically. By setting the time lag, k, to 0, the equation yields the constant variance of the process. Advancing the time lag so that k equals 1 yields the covariance between adjacent observations. For any time lag of 2 or more, the covariance drops exactly to 0. Because the model only looks backward one single step, observations separated by 2 or more periods share no common noise terms. This zero covariance translates directly into a hard cutoff on the model's autocorrelation function, or ACF graph. The correlation drops to absolute 0 immediately after lag 1. When you observe a hard cutoff like this in an empirical ACF graph, it provides the definitive mathematical fingerprint that the underlying data follows a finite moving average process. When identifying an MA model, we must account for the relationship between the model parameters and the resulting autocorrelation function. We can demonstrate this relationship using the equation for autocorrelation at lag 1. If you calculate this using a specific theta parameter and then substitute data with its exact reciprocal, 1 over theta, the formula yields the exact same autocorrelation value. This mathematical overlap means that two distinct models can generate the exact same statistical signature. Because the output is identical, we cannot distinguish between these different parameters from the autocorrelation alone. To resolve this ambiguity, we introduce the condition of invertibility. We apply this by recursively substituting the MA1 model into the past. Through this substitution, the finite moving average equation translates into an infinite autoregressive summation. For this inversion to mathematically converge into a valid finite sum, the absolute value of theta must be less than 1. Expanding this rule to the general MA to Q characteristic polynomial gives us a universal boundary. The roots of the equation must exceed 1 in absolute value. Invertibility is a mandatory boundary condition. It guarantees a one-to-one mapping between the theoretical MA model and the observable data, allowing for unique parameter identification.
While moving average models rely on unobserved noise, the autoregressive, or AR process, is a regression of the data series entirely upon its own past values. In the ARP model, the current value, xt, is a linear combination of past historical data points plus a single new white noise innovation term, keeping the model practically viable for prediction. Since AR models depend directly on their own past, extracting their observable autocorrelation signature requires a specialized approach. We extract this by taking the AR process definition, in this case an AR2 model, multiplying it by a lagged term, xt plus k, and then taking the mathematical expectation of both sides. This resolves into a system of terms based on the correlation coefficient, ρ. The resulting system is known as the Ewell-Walker equations. These isolate the specific correlation coefficients of the process. We can then contrast the output of the Ewell-Walker equations with the moving average model. Because the current state, xt, depends on xt minus 1, which recursively depends on xt minus 2, the correlation in an AR model ripples backward. It never hits absolute zero like the MA model. Instead, the autocorrelation function decays toward zero. Depending on whether the characteristic roots are real or complex, this takes the shape of either a continuous exponential curve or a damped sine wave. That infinite decaying memory is the definitive mathematical fingerprint of an AR process, separating it from the finite memory of an MA process. When we attempt to combine AR and MA elements into higher-order models, the algebra becomes increasingly complex. Managing infinite summations term by term is a significant logistical barrier. We bypass this barrier using the backshift operator, denoted as B. B is a linear operator that specifically shifts the time index of a series backward by 1 unit. Apply B to the k to xt, and you get xt minus k. Applying the backshift operator compresses those sprawling infinite summations into clean, manageable polynomials. The AR characteristic polynomial can now be cleanly expressed as phi of b, and the MA characteristic polynomial is expressed as theta of b. The backshift operator functions as a crucial translation tool, converting messy, sequential time data into standardized polynomial algebra. With our algebra standardized, we can finally merge the isolated autoregressive and moving average expressions into a single, unified framework. This is the master equation for the general mixed autoregressive moving average, or ARMA-PQ model. Phi of b times xt equals theta of b times wt. This combined model inherits the strict boundaries of its components. AR elements require stationarity, MA elements require invertibility. The diagnostic traits also combine. Purely MA signatures cut off abruptly, whereas purely AR or mixed AR-MA signatures decay toward zero. By merging these components, the ARMA-PQ equation captures complex dependencies that purely AR or MA processes cannot model on their own. Understanding these dual constraints and correctly identifying their specific autocorrelation fingerprints is the prerequisite for translating noisy, chaotic real-world sequences into predictable mathematical reality.